Our current goal for the next couple of videos will be to determine when an infinite sum of numbers turns out to be finite. Why do we care about determining when an infinite sum turns out to be a finite answer? Well, it's because I really care about understanding this function f of x, and I'd like to know when a function actually equals its Taylor series. So that's the objective of the next few videos. We've seen examples of this. So one example we've seen is the geometric series. Maybe I will do 2/3 to the n. This is the series 1 plus 2/3 to the first plus 2/3 squared, and so on. And we've seen that this infinite sum actually equals a finite number, in this case 1 over 1 minus 2/3. So this is a finite number. As another example, a kind of silly example, if I have the sum n going from 0 to infinity of 1 to the n, that's 1 plus 1 plus 1 and so on. This is not finite. So instead of saying finite and not finite, I'd like to give some terms describing these situations. So here is a definition. If the limit as m goes to infinity, the sum n going from 0 to m of an exists and is a finite number, then we say that the infinite sum, n going from 0 to infinity, of an converges. So that's what converges means. Otherwise, we're going to say that this infinite sum diverges. So converges means I get a finite answer when I do the infinite sum. So in this geometric series example, this is a convergent series, so converges. The example here, where I'm just adding a bunch of ones together, does not have a limit, which is a finite number, so this diverges. So in using these terms, our current goal is to determine when an infinite sum converges and when it diverges. So here is an observation. If your sum converges, if you get a convergent sum, meaning this actually adds up to a finite number, then the terms themselves, the things that you're adding up, have to get smaller. So the limit as n goes to infinity of an has to be equal to 0. So look up here as an example. 1 plus 2/3 to the first plus 2/3 squared. 2/3 squared is smaller than 2/3. These numbers get smaller. In order to get a finite answer at the end, you have to be adding smaller and smaller and smaller terms together. Not like this example. This example, the terms don't get smaller. There's no chance of you getting a finite number at the end. So that's the observation. However, warning. If the terms get smaller, So if you're adding smaller and smaller numbers together, then the sum, an, can still possibly diverge. So that's a strange fact if you've never seen it before. There's a classic example that we all have to know. So here's an example. This is called the Harmonic Series. The Harmonic Series is the series, the sum, n going from 1 to infinity, of 1 over n. So if you write out the terms, this would be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6, 1/7, 1/8, 1/9, 1 over 16, forever. This series, I'll show you why. There's a famous reason why, but this series diverges. The terms themselves are getting smaller and smaller and smaller. Yeah, I totally agree with that. But when you sum them up and you take this limit, you still get an infinite result, meaning these numbers can be as large as you want. So that's a strange fact if you've never seen it before, but the harmonic series 1 over n diverges. Here's why. I'm going to make this sum smaller. So I'm going to get smaller. I'm going to take this and I'm going to get smaller numbers. Here's how I'm going to do it. I'm going to start with 1 and 1/2. I'm not going to change those. But the next two numbers here, I'm going to replace the 1/3 with 1/4. So I'm going to have a 1/4 here and a 1/4 here. Then after that, the next four numbers, I'm going to replace every term with 1/8. So this will be 1/8 plus 1/8 plus 1/8 plus 1/8. So I got smaller because 1/8 is smaller than 1/5. 1/8 is smaller than 1/6. 1/8 is smaller than 1/7, and so on. Then I'm going to replace the next 8 numbers. There are 8 numbers between 9 and 16 inclusive. I'm going to replace all those with 1/16. So 1/16, all of the numbers in this group, 1/16. And I'm going to keep doing that. The next numbers I would replace with 1 over 32, and so on. Well, if you see what I've done here, I have 1 plus 1/2, and then 1/4 plus 1/4. These two numbers are equal to 1/2. 1/8 plus 1/8 plus 1/8 plus 1/8. I got 4/8. That's 1/2. In this circle, I'm going to have 8/16. Another 1/2. And you can keep doing this forever. So you'll end up with 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2. These terms don't get smaller. It's pretty clear that if you add up 1/2 an infinite number of times, you don't get a finite answer. So this is divergent. Divergent. It's a divergent series because you're not getting a finite number out. The series 1 over n, the harmonic series, is even bigger. So there's no chance I'll get a finite number. So that's divergent as well. So this is a famous example. You've got to know it. Harmonic series. The sum 1 over n diverges even though the terms themselves get smaller. So this is an interesting example, so much so I'd like to say a few more words about it. So on this page, I have written out the first 19 terms in the harmonic series. This diverges. We just saw this will not be a finite number. But what would happen if I crossed some of these numbers out? If I didn't add them all up, could then I get a finite answer? Well, this is somewhat interesting. Instead of summing over all integers, what if I just looked at the primes? So for this, I will add up 1 over p every time I have a prime number. So 1 is not prime, but 2 is prime, so I'll have 1/2 in there. 3 is prime, so 1/3. 5 is prime, so I'm going to skip 1/4 and do 1/5. Next term would be 1/7. 8, 9, 10, 11. So I'm going to skip a bunch of numbers here. I think I get 1 over 17, 1 over 19, and so on. If you skip every number that's not a prime, you still get divergence. I'm not going to prove this for you. It's kind of a famous result. It takes a little bit more machinery than I want to build up right now to prove. But still, this still diverges, which is somewhat amazing, meaning 1 over the primes still adds up to an infinitely large number. But I could do even better. What if I say I'm only going to add up p, where p is prime, and I'm going to say that p ends in a 9. So not only do you have to be a prime number, your last digit has to be a 9. So I'm going to skip every number that's, not a prime and does not end in 9. So the first number, if you look here, that I'm going to add up is 1 over 19. Is 1 over 19. The next number, I think, would be 1 over 29. I believe 29 is prime. And so on. This still diverges. That still diverges. Furthermore, I could do even better. If you say I want p to be prime, and I want p to end in 999 copies of 9, and I'm going to add 1 over p. I can't even think of a prime number that ends with 999 nines. So when you do the decimal expansion, the last 999 digits have to be a 9, and it has to be prime at the same time. I'm not going to write one down because I can't seem to think of one right now, but there are some. In fact, there are so many that this still diverges. It still diverges. So what I'm doing right now is trying to impress upon you that this divergent harmonic series is not even close to being convergent. In fact, if you throw out a lot of numbers, like if you throw out all numbers except the primes, or the primes ending in 9 or 999s, they're still divergent. So, I hope now it's starting to become clear that if the terms themselves go to 0, the sum can either converge or diverge. All right, great.